Hi there. This video is an introduction to the basic concepts of the practice of the finite element method. I will try to simplify this concept as much as possible. Hence the highlighted part in pink of the title. We start with the obvious question. Why do we use the finite element method? The answer is simple. To solve partial differential equations. The obvious following question will be, why the partial differential equations? Quite simply, because they govern almost all physical phenomena. I say almost because there are problems that are governed by simpler algebraic equations. The first basic concept we are going to talk about is the body. A body is said to be solid to differentiate it from a fluid. A solid body can be deformable, otherwise it is said to be rigid. If an elastic solid is subjected to a static loading, which can be a force or a torque, it deforms and then gains a static equilibrium. To study the static equilibrium of a deformable body by the finite element method, it is subdivided into several finite elements, which are numbered in circles. These elements are linked by also numbered nodes, but without the circles to differentiate them from the elements. The numbers of elements and nodes can be different, and they are in most situations. The way of numbering can be random, but it can give equivalent mathematical systems that are neither nice nor easy to solve. The element is only a mathematical relation which defines the variation of the geometry as well as the unknown function between the nodes. This relationship can be as simple as a linear or more elaborate functions. The connectivity table is an important tool. It contains the numbers of all the elements, accompanied by the numbers of their nodes. In the node section, a column is associated with each node. It should be noted that an element can consist of a single node. We take the simple example of the bar, which is made up of 6 elements and 7 nodes. I will separate the elements first. Then I start to fill the table. This is only to clarify the process. The first element is located between the first node and the second. The second element between the second node and the third. The third element between the third and the fourth node. And so on, until the last node. Let's consider another example. The first element is located between the first and the second node. The second element between the second and the third. Here we see that the third element is located between the first and the third, until the fifth, which is between the third and the fourth node. We now move on to another important concept, which is the number of degrees of freedom, which we can imagine as the number of possibilities of movement of a body. The finite element method is often applied to elastic problems. This is why we often speak of movement and deformation. However, the method can be applied to other physical problems such as thermal problems where degrees of freedom become temperature in different directions. So for a rigid body, which means undeformable, in a 3D space it can only make the following movements. A translation along the x-axis, another translation along the y-axis, a translation along the z-axis, a rotation around the x-axis, another rotation around the y-axis, and a final rotation around the z-axis. In total, a rigid body does not have more than 6 degrees of freedom. 6 at most, not more. However, it can lose or have fewer degrees of freedom if it is constrained or restricted in motion. The number of degrees of freedom of an element depends on the number of the nodes which compose it and their respective degrees of freedom. Because the nodes are independent in motion, the number of degrees of freedom of an element is equal to the sum of the degrees of freedom of the nodes which compose it. And that, whatever the number of these nodes, a deformable body theoretically has an infinity of degrees of freedom because it is theoretically composed of an infinity of particles. However, its representation as a set of finite elements, called the mesh, has a limited number, which is equal to the sum of the degrees of freedom of all nodes. I said nodes and not elements. Nt is the total number of degrees of freedom of the system. Nn is the number of nodes, and I is the number of degrees of freedom of the I node, where I is the number of the node. Solving a physical problem by finite elements transforms the analytically difficult, if not often impossible to solve, partial differential equation into a set of algebraic equations simple to solve. The size of the final algebraic system, which means the number of equations to be solved, is defined by the total number of degrees of freedom of the system, meaning Nt. For example, for a problem of static mechanics, the size or the length of the vector of the loads, force or torque or other, is equal to Nt, the size or the length of the vector of displacements, translation, rotation or other, is also equal to nt, the size of the total stiffness matrix, which is always square and symmetrical, is equal to nt in each direction, so nt times nt. The total matrix is assembled from the elementary stiffness matrices. Their number is equal to the number of the elements. The dimension in each direction of the elementary stiffness matrix is equal to the number of degrees of freedom of the element which it represents, which means Ne times Ne. The values of the elementary matrix depend on the physics of the problem studied and the various assumptions adopted, and they do not depend on the way in which the geometry is meshed. For example, a one-dimensional spring element, defined by the stiffness constant K, without the brackets to not be confused with the matrix, is represented by the following 2 times 2 matrices. Now we consider an example to show how to implement all these concepts. The example consists in finding the values of the two displacements x1 and x2 as well as the reaction Rx at the point of attachment of the system in static equilibrium. First, the domain is meshed or subdivided into 2 one-dimensional elements. Then the elements, as well as the nodes, are numbered from left to right. The direction is arbitrary. The numbers of the elements are circled, and those of the nodes are not to differentiate them. With each element is associated an elementary stiffness matrix which depends on the element's stiffness. All the loadings F as well as all the degrees of freedom are represented. The assembly of the global stiffness matrix is based on the connectivity table which defines how the elements are related to each other. The first element is located between the first and the second node, and the second element between the second and the third node. We have a mesh made up of 3 nodes, having 1 degree of freedom each, which gives a total number of degrees of freedom equal to 3. The size of the total stiffness matrix, and therefore 3 times 3. With the connectivity table already obtained, we start with the first element which is located between the first and the second node. Its elementary matrix is placed between the first and the second column, and the first and the second row. In the same way, the second element, which is located between the second and the third node, is placed between the second and the third column and the second and the third row. For the values that share the same position, we simply add them. The global rigidity matrix is filled with zeros in the remaining cells. The global system to be solved will be given by this equation. The resulting equation can be solved after being simplified by applying the boundary conditions. We eliminate the rows and the columns which correspond to the null values of displacement. Here is position 1. And we solve the system with the remaining values. A simple system of 2 unknowns and 2 equations. To calculate the reaction at the first node, we use the original system before simplification. The first equation is enough to calculate the reaction Rx. With this figure which summarizes all the results and on which we can check the static equilibrium, we conclude this introductory video of the applied finite element method. The next video will be devoted to a series of exercises on one-dimensional spring elements.